First of all, thank you very much for the organizer for inviting me. I really enjoyed this conference, and I also want to thank all the audience here for staying with me while there is England against Uruguay, and also we have lunch soon, so I'll try to be quick. So the talk today is about multi-reference alignment, and this is a statistical estimation problem. So let me just get straight to it. So in this problem, we have a group G of transformations that acts on some vector space X. So X is a space of objects. And what we'd like to do is to estimate a single element, little x of capital X, and a set of group transformations, n of them, G1 to Gn. So think of G as say as a Lie group or say an orthogonal group. And our measurements of the form that we take the element X, we rotate it by the group action by applying it to Gi, and then we have some linear operator P that I'll specify soon, and then it is corrupted with noise, epsilon I. So P is some linear transformation from X to Y, where Y is another vector space. Think of it as the measurement space. So in this problem, both X and the GIs are unknown. So it's a nonlinear estimation problem, and we'd like to estimate both. Now, clearly we can say, okay, let's try to do some kind of EM or alternating minimization. So if we have a guess for X, then it's very easy to estimate the GIs. And similarly, if we know the GIs, then estimating X is just solving some least squares problem. But as all of you probably know, we have no guarantees on alternating minimization and expectation minimization except for getting to some local optima. So what we'd really like to find is say if we try to solve this problem using maximum likelihood, say we have some model for the noise, then we'd like to have some algorithm that gives us the global optimizer. So let's see if in this talk if this is doable or not. So first let me try to motivate the problem, where this comes up from. So the first application is registration. And in the registration problem, you can think of, say, signals over the unit circle or images over the unit sphere. And every time you observe them with some rotation or translation, say, if it's on the line. So G in this case is, say, the special orthogonal group over the Euclidean space in D dimensions. X is, say, the space of band-limited functions over the unit circle or the unit sphere. And we have the left action, so we just rotate the function down on function h in this case. And our measurement is of the form that we sample the function over L specified points over the circle, over the sphere. And we have the image formation model, and we'd like to find both the unknown signal h and the transformation GIs. So here is a picture that illustrates this model. So we have for example, think of a problem, say, in radar, where you transmit a signal that you know what it is. So in this case, the template is known, and you'd like to estimate the time delay. So if the shifted template is clean or has very little noise, then it's very easy to find what is the time delay by just doing a correlation, the optimal match filter. But if you don't know what is the template that was transmitted and only see our say noisy reference signals, then you cannot do optimal match filter. If the noise is not too significant, like in the green example here, then again correlation should work. But if the noise is horrible and the SNR is very, very low, then pairwise matching between multiple signals would not work. So it will just give you garbage. But if you observe many of them, say if n is large, say much greater than 2, then maybe still you can do a fairly good estimation because you know that all of them contain exactly the same underlying clean template. And indeed, in this case, one can use invariance. So for example, the power spectrum is invariant to shifts, and so once you have enough noisy references, you can estimate the power spectrum. And there is also a generalization of the power spectrum to higher order spectra. It's called the bispectrum. And it allows us to do estimation of the underlying clean template up to a global translation or rotation. But it is not optimal in terms of sample complexity. And so what we would really like to do is to do maximum likelihood estimation. But the problem with maximum likelihood estimation is that it's computationally intractable. The search space for all the possible translations or rotations is exponentially large in the number of signals in n. So for every signal, we have to find its own rotation. And so, and also in other problems we don't have, that I'll mention in the next few slides, we don't have any invariants to work with. So the talk today is really how to do maximum likelihood estimation for this type of problems. So really the problem that I most care about is, it's a problem that comes from structural biology. I'll not get into all the details of the problem today, but it's called single particle reconstruction from Cryo EM. In this problem, the group of transformations is the SO3, the special orthogonal group in R3. X is just the space of, say, band-limited functions over R3. So it's a subspace of L2. And again, we have the left action, where you just rotate the function. And now, instead of observing the function over points, we have not just a sampling operator, but we have a more complicated linear operator, which is known as the discrete X-ray transform from perturbative tomography. And in the next slide, I'll actually, the next couple of slides, I'll show what it is. So again, it's a problem of this form where we have images, there are projections of rotating functions plus noise, and we'd like to find both phi and group elements. Another problem is in computer graphics. There are also problems in computer vision. So here, for example, X is our surfaces in R3, and the group of transformation is just a homomorphism or diffeomorphism between surfaces. Excuse me. And you'd like to do what is known as global shape matching between those surfaces. So this is a figure that I shamelessly stolen from Peter Wangen, who is a postdoc with Leo Grubas at Stanford. And usually the way people approach this problem is by taking a pair of shapes or pair of images, finding feature correspondences, finding the best permutation between shapes. But what we'd really like to do is somehow find a permutation which are discretization of the surfaces in a globally consistent way. That is not just doing pairwise matching, but actually take the whole set of surfaces or images and somehow do a global matching. So again, I'll show you today how this can be done. So in all these problems, there is one canonical optimization problem that one needs to solve at the end that has the following form. So it's a nonlinear optimization problem where the cost function is a sum over pairwise interactions between the group elements, the gi's and the gj's. The functions, the fij, depend exactly on the pair of shapes or the pair of images and so on. So it can there is dependency on the specific I and j. So solving a three-dimensional puzzle is an example of this problem. So every piece of the puzzle, you need to locate it over the sphere and also find its in-plane rotation. So to every piece of the puzzle, there corresponds an element of SO3. Now, two pieces of the puzzle cannot overlap. So the potential function is like infinite. You have a Hart-sphere interaction that you don't want it to overlap. When they are far apart, say the potential is 0, you don't care. And when they touch each other, well, now it depends on the color and the shape. And all this information is encoded in this Fij. And now we'd like to find a solution that minimizes this cost. And there are other applications that I'll not speak about today. So somehow we'd like to find a way to globally arrange data and find a solution that is globally consistent. So the problem in single particle reconstruction is the following. So we'd like to find three-dimensional structures of molecules. And in this particular application, the way this is being done, you flash freeze many copies of the same molecule in a very thin layer of ice using liquid nitrogen. And the ice layer is so thin that if you look at it in the vertical direction, you'd see one molecule at most. So no two molecules can actually occupy the space vertically. And at the moment of freezing, every molecule just picks some random rotation and random position inside the ice layer. And then you take two-dimensional projection images of the 3D molecules by shooting an electron beam at the specimen. The electron beam goes through the ice layer and the molecule, if there is a molecule there. And beneath you have a film or a camera, and the pixel intensity is proportional to the line integral of the electric potential created by the molecule. So the molecules are just a bunch of charged atoms. And so what you get are 2D projection images of the 3D object. So this is a micrograph. This is just an artist's concept. It's not a real micrograph. The first step is just to do particle picking, to do image segmentation. So you cut little red boxes that contain particles, and then the goal is to find a 3D structure from these 2D projection images. So here, phi is the electric potential of the molecule. It's a function of x, y, z, say a function in L2 of R3, or a band-limited function. And what we observe are projection images. So here is the image formation model. It's just the line integral of the potential function phi after you rotate it by some unknown element of SO3. So this is exactly the multi-reference alignment model that I discussed before, where the projection operator P is the discrete X-ray transform. And so the cryo problem is or the single particle extraction problem is to find the electric potential phi from the n images. But here we don't know the group elements, R1 to Rn. So from this problem, I assume or neglected the problem of finding the translations. That is much easier to solve in this problem. I'll not get into it. So here is a toy example. So suppose that I give you, say, 12 projection images that look like this, and the goal for you is to find the 3D object. So here maybe you've all seen enough Disney movies when you were kids, and you can make clever guesses of how the 3D structure looks like. But in reality, the images are very, very noisy. So here is a sample of 4 projection images out of a much larger collection of 27,000 projection images. So these are real experimental images. So if you stare at it for a long enough time, then you might be convinced that there is a signal here. So near center, you'll see that the pixels are somewhat brighter. And that's actually how they do the particle picking. And let me try to convince you that the signal is there. So now I'll show you a 3D reconstruction that 2 of my students, former students, and Hui and Jane did. So in yellow, you see the ground truth. So this molecule is a subunit of a larger molecule called the ribosome. We know the X-ray structure for this molecule. For example, so in 2009, the Nobel Prize was awarded for finding the structure of this molecule using X-ray crystallography. And in white, you see a reconstruction from the same 27,000 experimental projection images. So I hope that this convinces you that the signal is there, and we do a fairly good job in finding the structure. I'm cheating a bit because the resolution here is not as good as what one can get using X-ray crystallography. But still, you see that the signal is there. Now, I don't have enough time to go over the whole pipeline of how this is being done. I just want to focus on how we do our potential estimation, that is, how we find the group elements, the rotations. And you should be aware that we're a bit unique in that because 99% of the cryo labs around the world are just doing iterative refinement, which is doing the same alternating minimization process that I described at the very beginning. That is, you guess the structure of the molecule, then you find the rotations. When you find the rotations, you can get a new guess for X by solving the least squares problem. So the way that you can estimate the rotations is using a fundamental theorem from computerized tomography, which is known as the Fourier projection-sice theorem. And what the slice theorem says, it is a relationship between the 3D Fourier transform of the molecule and the 2D Fourier transform of the projection images. And this relationship is stated as following. So on the one hand, you have the 3D Fourier transform of the 3D molecule. And on the other hand, you have the 2D projection images of the 2D projection images, and you can take the 2D Fourier transform. And what the slice theorem says, it says that the values of the 2D Fourier transform of the 2D projection images are nothing but the restriction of the 3D Fourier transform of the molecule to a planar slice that goes through the origin in the reciprocal space, in Fourier space. And the rotation of this slice is exactly correspond to the rotation. That is, it will be perpendicular to the viewing direction. And that's actually how computerized tomography in medical imaging works. So if a patient needs to do a CT scan, then the patient is being told not to move for the duration of the imaging process, and then the machine would scan, let's say, the brain from different directions. And it's very important for the patient to rest still so that the directions are known to the scanning machine. Otherwise, if the patient would be constantly moving, then the viewing direction would be unknown or be ambiguous. So now, because that you know that every slice, every projection image corresponds to a slice that goes to the origin, then you can populate the 3D Fourier space and then do 3D Fourier inversion and get the 3D density map of the patient's brain. But in the single particle reconstruction problem, we don't know the viewing directions. We don't know the rotations. So we know that we have slices in 3D Fourier space, planar slices, but we need to organize them in some way. They're unorganized. But the slice theorem now gives us a way of doing it because there is a simple geometry that we're all familiar with probably from elementary school or high school, that if you take two planes in R3, they are going to, unless they are parallel to each other, they are going to intersect at a line. So this is known as the common line of intersection, which means that every two Fourier transforms, say of image I and image J, are going to intersect at a line, meaning that the values of the 2D Fourier transforms, say on the red line here, on the red line here, are going to be exactly the same. So one can find this, if the images are not too noisy, one can go ahead and find this pair of lines, the common line, by just, say, doing brute force, say, normalized cross correlation between every line in image, in the Fourier transform image I with the Fourier transform in image J. Once you find the line, then you know how the two planes intersect, but you still don't know the angle between the two planes. So there is 1 degree of freedom which is left undetermined. And in the 80s, both in the West and in the East, people have suggested how to determine this remaining degree of freedom by just adding a third plane. So once you know the common line of intersection between 3 planes, then it uniquely determines their orientation up to a global rotation of the molecule and also up to a global reflection. So that's why in the Mickey Mouse I put a ball to the right. In the reconstruction, it can also appear to the left. So this is known as angular reconstitution. And let's see if it's a viable method. So here I'm doing a simulation where I took a clean projection image, and now I'm adding Gaussian additive white noise to it at different level of signal to noise ratio. So maybe 2 to the minus 6, 2 to the minus 7 is what you see in the experimental images. And here I show you the detection rate of common lines. So how many times we actually detected the common line correctly. And you see that maybe 2 to the minus 6, 2 to the minus 7, only say 10% of the common lines are detected reliably. And so this means that you should be extremely lucky to take 3 planes and get have angular reconstitution work properly. And which is the same problem that we mentioned before with registration. When we have very high noise, then comparing pairs is not a good way to go about this problem. Really what you want to do is to use all the signals or all the images at once. And so angular reconstitution tells us about the geometry of the problem, but it's not a viable method to solve the problem with noisy images. So instead, what we'd like to do is how to do maximum likelihood or quasi-maximum likelihood. That is, what we'd like to do is for every possible guess of rotations, R1 to Rn that correspond to the images, then we know what are the common lines implied by those rotations. We can look at the images and just check their agreement, because we know that there should be common lines. So, for example, if the noise model is Gaussian additive noise model, then we can give a likelihood. Just say the Euclidean, the minus log likelihood will just be the squared Euclidean distance between the values of the 2D Fourier transform on those lines. the problem that it's computationally tractable. So I'm going to enumerate over all possible n rotations. So for those of you who didn't follow so far, now is the time to wake up, because now I'm going to reveal the main idea, how we're going to do it. And the main idea is to do something very crazy and to lift SO3 to the permutation group over the sphere. So the way we do it, we discretize the sphere by placing L points over the unit sphere in R3. So omega 1, omega 2, and so on. So you can distribute it nicely, say, using a spherical T design. So it's a nice distribution of points over the sphere. And once you rotate the sphere, then say the black points will rotate into red points. So for example, omega 1, which was here, will be mapped to, say, g of omega 1. G is the rotation. Omega 2 will be mapped to g omega 2, and so on. And now I can assign to this rotation a permutation. So for example, we see that g of omega 1 is close to omega 6, so the permutation will take 1 to 6. And g omega 2 is close to omega 8, so the permutation takes 2 to 8, and so on. Now, of course, there can be ambiguity, so maybe, I don't know, is g omega 3 is closer to omega 7 or omega L? So we'd like to find, say, the best permutation, say, least square sense or some way. So to go from here to here, maybe you need to solve an assignment problem. You can do it in linear programming. And to go in the back direction, so if you know the backward direction, if you know the permutation, finding the best orientation, you can solve a Procrustes problem. But don't be bothered about it, because we're not going to do it explicitly at no step. So just think of it a Gigankian experiment, okay? So we can do this correspondent in our head. So every element of SO3, we can correspond to it a permutation over L elements, where L is our discretization of the sphere. Now this lifting, why am I doing this lifting? Because it's going to make the very nonlinear log likelihood function. Remember, the sum over all pairwise of Fij, Gi inverse Dj is going to make it linear. If we have time, I'll show you how this is done. But first, I need to show you how we're going to convexly relax the search space, because still permutations are not very amenable to optimize over, because are not, they do not form a convex space. So to convexify them, well, it's quite easy. We know that the convex style of n factorial permutations is just the set of doubly stochastic matrices. So matrices with entries that are non-negative, sum of rows is 1, sum of columns is 1. So this is known as the Birkhoff von Neumann polytope. So mathematically, it's written here. But it sounds that the relaxation is too loose. I mean, if you look at this picture here, not every permutation corresponds to an element of SO3. So say that if we have, I don't know, if this is San Francisco and this is Berkeley, and once we do the rotation, it's impossible that San Francisco will be mapped to, I don't know, Moscow and Berkeley to Rio. Okay, so we want nearby points to be mapped to nearby points. So more specifically, we know that SO3 is an isometry, so it preserves inner product. So if we look at the Gram matrix of our points in our design, then after rotation, then say point omega 1 is mapped to omega pi I, and omega j is mapped to omega pi j, then the inner product between, let's go here, the inner product between, say, omega 1 and omega 2 is the same as the inner product between g omega 1 and g omega 2, because it's an isometry. So we have after the discretization error, that the points do not collide with our original points, then we have that omega ij is just omega pi j. And in linear algebra notation, it means that once you conjugate omega with the permutation matrix from left and right, you get omega b. Or because the permutation matrix is also an orthogonal matrix, you can multiply by pi and get that pi omega is omega pi, which means that omega and pi commute. So we started with the Birkhoff von Neumann polytope of doubly stochastic matrices, and now we can see that we can slice and dice it with many linear constraints that correspond to the commutativity of omega and pi. So this is just many linear constraints that we should add, and this corresponds to the fact that we have not any permutation, but actually permutation that come from isometries. Also, you can add the fact that it's SO3, that is, it's a special orthogonal group. It preserves orientation. And by the Euler's rotation axis, you can add the constraint that we know that there are 2 points that are, okay, fine, that are invariant. I mean, they remain fixed by the rotation. And so the trace of the permutation matrix should be at least 2. Now, notice that in terms of computational complexity here, it is important to know that we are discretizing the sphere and not SO3. That is, even though we care about finding rotations, I'm discretizing the space on which the group acts and not the group itself. So in this way, we gain 1 dimension, which is very important in our discretization. So the 2 sphere instead of SO3, which is 3 dimensional. So now let's put everything together. There is still one thing which is missing. So I can do this discretization for every pairwise permutation between rotations I and j, but now I need to add consistency. That is, if I know the rotation from I to j and the rotation from j to k, then the rotation from I to k is not arbitrary. It must be the product between the 2 rotations. And so to add this consistency, okay, so let's introduce this matrix G. So G is going to encode all the pairwise permutations. So it's an n by n matrix where every entry is by itself a matrix of size L by L. It should be this permutation matrix of size L by L. And we want them to factorize that Gij will be of the form pi I pi j transpose. So think of pi I as the permutation from, say, one canonical frame over the sphere. And then Gij should be pi I pi j transpose, from which you immediately see that G is a positive semi-definite matrix. On the diagonal of G, we have identity blocks of size L by L, and the rank of G should be L. So the only thing that we cannot handle is the rank constraint because it's non-convex, so we'll drop it. And so if we put everything now together, we see that the third space is the set of matrices of size NL by NL that are positive semi-definite, that have identity blocks on the diagonal. This encodes the cycle consistency. All the blocks are doubly stochastic, so Gij, all the entries are non-negative. Sum of rows, sum of columns are 1. And on top of it, we know that they're not just any double stochastic matrices that come from SO3, so we also have the commutativity constraint that we have before. If I drop the last constraint, then this is exactly the same semi-definite program. I didn't show you the objective yet, that appears in the work of Moses Charikar and the Makarichev brothers for solving the unique games problem in theoretical computer science. So I still need to show you that the cost function is actually linear. I'm afraid that we don't have time for it. So any of you that want to learn about the details, I'm very happy to discuss it later on. But again, this entire game of lifting to permutation was to allow to write this very nonlinear cost function in a linear way that you see here. So it's linear in the gram in the matrix G. And this matrix of Cij just depend on the data that you have. So this is what we have in the common lines problem in Cryo. So I would like to wrap up by telling you about an experimental phenomena, empirical phenomena that we see, and this is why I think this type of relaxation is very interesting. And what we see experimentally is tightness of the SDP. By tightness, I mean the following, that, okay, so we did this relaxation, and we got a solution. Who tells me that the solution is actually going to be permutation matrices and of the desired rank, of rank L. And so what you see here on the right is the x-axis is just the noise level sigma. The y-axis is the fraction of times in which we actually got the desired rank. And the solution was an integer solution of 0, 1 for permutation matrices. And you see that up to some noise level, with probability 1, we get that the SDP is tight. Basically, it gives us the maximum likelihood solution because we did a relaxation. So if I find a solution of integer form and a desired rank, that I know that it's the maximum likelihood. So unlike alternate minimization or EM, that all you can say that you find some local optimizer, here when the SDP give you a solution of some form, you know that you have a certificate, it is the MLE. And for a wide range of problems that we also didn't discuss here, like general orthogonal processes problem, we see the same phenomena of phase transition, that up to some noise level, we get tightness of the SDP. So it's a viable method for finding a maximum likelihood solution for certain type of optimization problems. We still need better theoretical understanding of why we get this phase transition and why we see tightness of the SDP. And also, as probably many of you know, SDP does not scale very well to large-scale problems. So right now we're using ADMM, but there may well be better ways of solving this kind of optimization problems. References are listed here, and most of this work is done with collaboration with my student, Afonso Bandera, and Moses Charika, with a colleague at the Computer Science Department at Princeton University. Andy Zhu was a senior student at Princeton who graduated a year ago, and I would like to thank all of you.